Yeah, good. Yeah. Hi. Hi. Good afternoon. We're going to start the discussion of the physical vapor deposition for this lecture. Let me first give you a very broad picture of how we can do thin film deposition. As normally, if you think about it, this is the first step if you want to do anything on the silicon substrate, right? So, unless you want to etch into the substrate of silicon itself, you want to deposit something, for example, an oxide layer or metal layer or something before you want to do any patterning. So there are two general category of the deposition. One is we call it chemical vapor deposition. So basically, it's like cooking, like you have all the ingredients in it there, right? So you introduce the reactant gases into a chamber. This usually can be a vacuum chamber, and then there will be a chemical reaction that produces a film which is deposited on the substrate. So the key thing is that there's a chemical reaction happening inside the chamber. The second category basically is we call it physical vapor deposition. So basically there's no chemical reaction. So if you want to deposit a nickel, so you want a nickel target or a source of nickel solid. So for example, you can do heating, a solid until it evaporates, or bombarding with ions to sputter the sources in the plasma. So we will discuss both in this lecture. They're typically used for metals, but they can also deposit like dielectrics, like silicon, nitride, or other materials. Also for the physical vapor deposition, there are two general methods. One is called evaporation, and the second is called the sputtering. So we will limit ourselves to these general methods in this lecture. So let's look at the physical vapor deposition first, which we show on the right. This is a very simple schematic. So we will see that there will be a source, metal and that material that usually needs to be heated right here. And this will somehow generate an atomic flux, and we will be putting our wafer facing down, looking at this source at a certain distance. And generally this entire system is enclosed in vacuum. So let's first answer the question why we need a vacuum, right? So basically, if you generate, we know that the air is filled with a lot of the molecules. Now, if you think about it, we want the atom, once they leave the source, we don't want it to collide with other molecules or atoms. So in order to create, quantify, we actually define a parameter called mean free path. This is defined as, as an atom or a molecule. How long can it travel without colliding with another? So basically, this formula, if you look at that, depending on the K, which is a Boltzmann constant, T is the temperature. What's in the denominator is really the P, which is the pressure, and A is basically molecule diameter. If you look at that, it's pretty much inverse proportional to the pressure. So which basically makes sense. The lower the pressure, or the higher the vacuum, well, there's less molecules there, right? So basically, it can travel long enough before it collides with another one. So if we plug some typical numbers, A is about 2 to 5 angstrom. P basically is 1 to the 10 to the minus 4 Pascal. And then you can calculate that the mean free path is about 60 meters. So that's actually pretty good vacuum. In this way, we can guarantee that once a molecule basically leaves the source, it can travel to your wafer which is generally, about 20 to, 20 centimeter to maybe half a meter or even 1 meter. So this we can guarantee in, at least during the path, there's really no collision with any molecules. And this is also important because we don't want any, sort of contaminants that can also go in there. So the lower the pressure it is, the less sort of contaminant molecule or atoms in the system. So then we will turn our focus to how we generate this atomic flux. You can do in two ways. One is that you can heat these the material using a resistive heater, and this works well for a lot of organics and all other low melting temperature materials. But what if I want to evaporate this carrier or this boat itself, right? Sometimes the boat can be made by steel or others, right? What if I want to evaporate steel itself? Well, there's not really something else that can hold it and melt the steel without melting itself, right? So we actually can use what we call as the e-beam evaporation source. So let's look at how they are made. So to be complete, we basically revisited the thermal evaporation. We basically show some picture that those are the boats that hold the material, and then you heat the boat, and then the organic materials basically evaporates. But the other one, what we really want to focus on is that what if we want to evaporate the metal itself? For tungsten, for example, it has very high melting temperature, like almost 3,000 Kelvin. At that temperature, there's nothing that can hold it without being melted first. So what we do here is we are not really heating from the outside. So we have a crucible that holds the metal, but this thing doesn't get melted. But what we do is we actually inject electrons. So basically, we have a filament or electron gun that basically emits the electron, and then we send a very strong magnetic field, and we know that for the electron that come, moving in the magnetic field, it actually bend its trajectory. And doing that, we can actually sort of bend the electron, and once those high energy electrons are injected into a metal, they create a significant amount of heat. Think about it just like you are shorting a metal, right? Shorting a metal wire through the batteries, and basically you get very high energy electrons basically melt the metals. It can melt pretty much everything, as long as you have high energy electrons and just keep impinged for a long time. On the other hand, we will look more into this. This is a similar picture showing more like realistic what it looked like. So we have this crucible, and we actually have cooling waters. So if you think about it, the electrons basically coming out, this is the trajectory of the electron, striking the metal, and this basically you have a melted metal inside it. But when it reaches the crucibles, basically the crucible basically are cooled by the water. So really, this is how things we can actually make that we can actually melt the very high melting temperature metals without hurting the container itself. So this is a very versatile setup. It is capable of depositing a variety of metals. It can be a lot of metals. You can also use the same method to heat up the dielectrics, for example, silicon dioxide. And organics, you can also do that, but organics you need to be a little bit careful because the high energy electrons may break the molecule as it is heating it. So, and then secondly, we want to also show that you can build in what we call a thickness monitor Basically, it's the pink little rectangle that is mounted at the same distance from the evaporation source. And basically, if you can somehow calculate the amount of thickness that you gain at that location, then you can actually infer that how much thickness of the material that's deposited in your substrate. So the film thickness control is done by acoustic resonance frequency shift. So think about it: if you have a string, like and if you vibrate the string, and depending on the mass of the string, you can actually change its vibrational frequency. So we won't go into too much details, but there are a lot of the parameters that you can input by that can calibrate that thickness monitor and give you a relatively accurate amount of the material or thickness of the film you will get. Let's look briefly the evaporation rate. We'll look at two things. One is the material loss rate from the source, right? And then we will also look at the receiving material received at the where the wafer is. This can be calculated relatively straightforward. Basically is the first in the parenthesis is basically mass, atomic mass, and some constant. And then we want to look at the vapor pressure at temperature T. So you can look at that. Certainly, the higher the vapor pressure is, the faster the rate is. So if we look at the diagram on the right-hand side, generally, if you look at the typical like aluminum, you don't really need a lot of the temperature. Basically, it will get you very high vapor pressure. So you can actually evaporate aluminum at a relatively lower temperature for a reasonable rate. Sometimes, if you look at that, tungsten, molybdenum, those are metals that are difficult to evaporate because even if you heat it up to over 2,000 degrees C, you get a relatively low vapor pressure for molybdenum, and for tungsten, 2,000 C doesn't even get you anything. So those are some of the metals that are difficult to evaporate, but it's still possible. But this basically asks for questions of what if we want tungsten and the molybdenum? They turn out to be important metals for the integrated circuits or solar cells, for example. And so we look at some alternative, because if you just use evaporation, it's going to be difficult, and it also basically requires a lot of the energy. So we'll look at that in the next couple of slides and also the next lecture. So for example, tungsten can be done by chemical vapor deposition, and molybdenum can be done by sputtering, etc. So what I want to call your attention to is that the amount of the material loss can be calculated by the vapor pressure of the metal. The amount of, or the deposition rate, is inverse proportional to the square of the source to wafer distance. In this case, is the R. This makes sense, right? Because the further away you put your wafer from the source, the more sort of the source material basically diverges, and you capture less amount of the material, and hence less thickness. So this is relatively straightforward, but there are reasons sometimes that you want to put your sample a little bit far away from the source. So let's take a look at this, what is the difference between the thermal and the E-beam evaporation. So the thermal evaporation can work with organics and less heat conducting materials with low melting temperatures. The E-beam evaporation, it has what we call you can make it a point source. So when we look at that now, the E-beam is also capable of, we call it, a broader evaporation area. But for the thermal evaporation, there's really no way to say, okay, I want all the materials coming from a point, right? You are heating the boat and everything comes out. For the E-beam, you can actually scan the electron beam so that the heating area is large. But you can also say, okay, I'm not scanning the electron beam. The electron beam is hitting a spot, always hitting the same spot. Of course, you will drill a hole very quickly into the metal, but there's a reason why we want to do that. And we will see that if you focus your evaporation to a tiny spot, what that does is that it will create a line of sight deposition. We will see that in the next couple of slides. It's very suitable for the process what we call a liftoff. Then it also, for the E-beam evaporation, as we see that you can actually calculate the do the evaporation rate control better because, well, you can heat it and cool it quickly by just shutting the E-beam off. But you can also do the thickness control by putting a shutter, above the thermal heating or thermal evaporation source. So both you can do relatively good control. So now let's look at why we want to do the evaporation from a point source. This typically is done what we call a liftoff process. So what we see here is that we first do a lithography. We just discussed this process before. And now after the development, now we can do a metal evaporation. In order to do that, relatively well, we need to have a point source because if the evaporation is from a broad source, then you can imagine that there will be a lot of the deposition toward the sidewall. In this case, in the liftoff process, we don't want any of the sidewall deposition because that will basically connect the metal on top of the photoresist and at the substrate. So the point source would allow us to do a line of sight deposition, which basically prevent the deposition at the sidewall of the photoresist. And as you can see that the disconnection between the metal on top of the photoresist and at the substrate, they need to be disconnected. In that way, when we remove or dissolve the photoresist, we are left with a metal pattern that sticks to the substrate. The liftoff process is also very, very versatile. On the other hand, they are not very broadly used in semiconductor manufacturing, but rather is very useful for university research or just a small production runs. So there are quite some advantages of this liftoff process. One is that it has high resolution. To the first order, only lithography limits the line width. So how good you can do the lithography, I can basically create or move the pattern into the metal. The materials that are difficult to impossible to etch can be patterned by the liftoff. For example, gold. As we know that gold is inert or noble metals, they don't react with a lot of the chemical agents, and that's why we love gold. Right? It can stay there forever. But that means it's very difficult to pattern it, and we can do liftoff to create the gold patterns. You can also do multi-layer film patterns as easy as single layer. So basically you just do an evaporation and cool it down and rotate your source and basically replace the source without breaking the vacuum, and you can do multiple layers of evaporation. A less obvious one is that the substrate basically are not etched or damaged in the liftoff. But some minor things that keep in mind is that the E-beam evaporation actually generates hot X-rays because of the high energy electron. When it hits the metal, it actually creates all sorts of reactions, and some of the X-rays does happen. Also, but those can be removable by annealing or avoided by using a thermal source. Secondly, the substrate being away from the heat source by about half a meter, the substrate actually can be kept at a relatively low temperature. Now, still, it will feel the heat from the source, but generally it doesn't raise too much temperature. This is important because your photoresist needs to be kept cool, otherwise it changes, it deforms at high temperatures. So now I have finished the discussion of the evaporation very briefly, and hopefully the general impression is that it's a very simple process. It can evaporate a lot of the materials, and combined with liftoff, it can actually create patterns in many, many different materials. So now I'm going to switch the gear and try to discuss plasmas. As we mentioned, that as versatile as the evaporation is, they are not a very commonly used in semiconductor manufacturing. But the plasma or the sputtering deposition is indeed widely adopted by the manufacturing of this integrated circuit. So you may ask why, right? So before we answer the question, we want to discuss plasma, because all the sputtering processes and also etching processes requires the generation of the plasma. So many of you may have some general sort of very probably general impression of what a plasma is, right? So the plasma basically is a dilute ionized gas. So many of the light bulbs basically contains a plasma. Basically, if you think about it, if you keep heating a gas, right, to a very high temperature, and they all have high energy, and somehow, this is, they can be called plasma. But what we want to show here is that this is a sort of a well-controlled plasma that we want the plasma to do its work. So let's first, try to form some pictures of the plasma. So I will first say it's a dilute ionized gas. It cannot have very high pressure, and also it cannot have very low pressure. It contains very free electrons and positive ions because the plasma itself is charge balanced. So if you have 1,000 electrons, you are going to have 1,000 positive ions to balance it. And it does conduct with the current mainly carried by the electrons. So it is not so high conductance so that it can completely block the RF energy, which is necessary to sustain the plasma. We will try to explain what it is. So the plasma density, and if you look at some of the tools, some of the tools will try to advertise, say, okay, this is a high density plasma tool. So let's look at what it is. So at a 5 millitorr, the total particle density is about 10 to the 13th particles per centimeter, a cubic centimeter. For low density plasmas, you have 10 to the 8th ions per cubic centimeter. High density is 10 to the 12th. So this is a very high number because if you look at that, that means every 1 out of the 10 particles is ionized compared to the 10 to the 13. And it is much higher a density than the low density plasma, which is almost 4 orders of magnitude higher. So also we want to show that the sheath basically is formed to shield the interior from the fields. And for the plasma region, it's actually field-free and approximately neutral. So we'll try to understand what this means. So let's look at one of the plasmas, and this typically, if you look at that, in order to sustain the plasma, you need to have an electrode, a pair of electrodes, and we call it either cathode or anode. And what it does is actually it established a field so that a charged particle can see the field once it is ionized. And generally, the voltage is about 1 kilovolts, certainly depending on the separation of the electrodes. But what we want to show that is that if, for example, what happens is that if one atom somehow gets ionized, we'll explain why it is ionized. Okay, but just hold on for now. Once it is ionized, then basically the electron is going to go towards the anode, which has higher potential. The electrons, because it's so small, it basically does not do any additional damage, if you think that way. But the positively charged ion, for example argon, they get accelerated towards the cathode. And this guy is the one that actually creates or sustains the plasma, because this guy, once charged, it has enough momentum. When it hits a neutral atom, it can do a few things. It can either sort of have enough energy so that it will ionize the neutral atom that it bumps into. Now if you keep doing that, it's going to be a chain reaction, because now you get a more positively charged ions. And if I kind of, you can think about it as an infective disease, right? If I somehow contaminate it, contagious, I, conveyed this to another person, and this other person continue doing that. And this will increase the density of the charged particles. The more it has, the more damage, or the more ionization it will incur. So, but this thing, like all the contagious diseases, they will be contained. And it turns out that the plasma can only sustain for certain pressures, right? And we claim that it's between 10 millitorr and 100 millitorr. And we will try to explain why this is the case. So we'll look at the pressure, and basically we'll look at the particle energies in this plasma. For certain pressure, we'll say that spacing between the molecule is 0.15 microns. And what happens is that for the thermal velocity of argon, we can calculate it about 1 kilometer per second, and that is at the pressure of the 10 millitorr level. And then we can calculate, because the spacing between molecules and the velocity, we can calculate what the velocity that the argon and the electron that can gain by having this amount of the electric field. So basically we can calculate, the argon can reach 400 kilometers per second before the next collision happens. Electrons are even faster. It goes to 10 to the 7th meters per second. So this turns out that you can actually gain substantial amount of energy. The shorter or the lower the pressure, right, it is, the more argon can gain the more energy the argon ions can gain before it hits the next body, right? So in this way, you may think, okay, low pressures help to generate and sustain the plasma, right? If the pressure is too high, basically I didn't get enough energy, and then I bump into another guy and I lose some amount of energy. So high pressure is not good for generating or sustain a plasma. So now, basically, if we look at the plasma, it basically have about, generally the majority of the neutral atom has about 1 kilometers per second in its thermal velocity. The argon ions has about 400 kilometers per second, and the electrons is much faster, 10 to the 7th meter per second. These basically, dictates a lot about the, characteristic of the plasmas. So we will argue first that the plasma is highly conducting due to the electrons. This is relatively easy to understand because, well, even though the electron is very light, but it carries the same amount of charge of the positively charged ion. They're both carrying one sort of electron. And if you look at the density, the current density, well, it's calculated by the density, and which doesn't matter whether it's electron or the positive ion, and the charge per charged particle, it's the same, and it's related to the velocity, right? So the electrons has about 200 times higher velocity than the positive ions. Of course, it basically occupy or presents the majority of the conductivity. So the plasma is highly conducting due to the electrons. And now we want to go back and say, okay, what happens is that the plasma can only be sustained in certain pressure ranges. So basically, if the pressure is too low, there's a lot of the energy that the argon basically ions accumulate. But the problem is that it doesn't find the next person to convey the energy to, right? So if the pressure is too low, basically the argons are accelerated, but they just didn't find anybody before it hits a wall, right? Because it's going towards the cathode, right? So if it doesn't find anybody, and basically the ion is annihilated at the electrode or the chamber, and that basically, well, all the positive charged ions are basically gone, and then you don't have the plasma. On the other hand, if the pressure is too high, well, then you just don't gain enough energy before the energy is lost to the bodies, and of course you don't ionize the bodies. So again, you don't have it. So this also changes, when the high density plasmas come into play, which we will briefly discuss later on. So now we have a little bit better understanding of what's happening inside of the plasma. Basically, we know that, okay, the plasma can only be sustained in certain pressure range, 10 millitorr to 100 millitorr. And then it's also conductive. The plasma is conductive. But that doesn't really answer any questions why we like it, right? Why does the semiconductor industry love the plasma, right? What does it do? And what I want to show you is that this important part is look at this, the potential of the plasma. And the important part is that if you look at the plasma, you see, this actually our light, is part of the plasma glow. So if you look at the plasma, you will see that there's something lighting up inside the plasma. This actually is what I would call it unsuccessful collision. So what happens is that if you want to sustain a plasma, you want the ion to hit another electron out of a neutral atoms, right? Because now you get a more positively charged ion and electron. But what happens most of the time is that they collide. The other guy is, I'm not going to give up my electrons. What happens is that this atom is excited. But in order to relax to its sort of ground state, it emits a photon, right? So this is where you see the light coming from. So the plasma does give out light, and that's why we use it, right? Before the LEDs occupy all the lighting business, right? So this is one of the, so that's where we see. But this is, again, not what we want. What we like so much is in the sheath area. And as we have discussed that the sheath, you can think about it as, this is the area where we actually kind of enclose the plasma. And if we look at the potential, inside of this glow region, in the plasma region, the potential doesn't change. And so basically it is more or less a neutral region, but there are basically electric field and potentials built up towards this, very close to the target or the cathode region. So we will try to explain what it is in the next slide. But basically, the plasma will establish a voltage difference, a potential that goes towards the target. Now, let's first hold off to explain why it existed, but just look at what this effect will do. What happens is that if for an argon ion is positively charged, if the argon ion is coming into this region, it gets accelerated. And what happens, you can think about the argon basically when it coming to the target, it doesn't go like landing of on very different angles or all sorts of angles. It all comes in normal to the substrate. In the meantime, it has energy, and this is very helpful because we want to later on when we discuss the etching, we want the etching gas to coming in with all this normal to the substrate, and this way we have a kind of we call it anisotropic etching. So we love the plasma because the plasma have the positive ions coming in all normal to your substrate, and has enough energy that can etch the substrate or the films. Next, let me try to explain how the sheath comes up. And what we want to show is that this is the potential that's existing in the sheath region is caused by the velocity mismatch between the positive ion and the negative electrons. So if you think about it, it's similar to the p-n junctions. So, but let's put it aside for now. But first, let me try to explain is that, let's say, first I cannot do that, but let's assume that there are 100 positive ions and 100 electrons. They're both stationary, right? And that basically allows us to maintain the neutrality, right? Neutral room. But the problem is that once they are moving, the electrons are moving 200 times faster. And then the positive ions coming much slower. And what happens is once the electron is generated for whatever reason, it basically just go right away. And as a result, there will be a net positively charged region in there. Hope that makes sense, right? Because the electron simply goes much faster. And this is we call it electron depleted region. Now this is a different, slightly different from the depletion region in the p-n junction because those ions are all still mobile, right? So you can see that because of high velocity, the electrons are gone much faster. And now what do you think about it? That once it goes away into the plasma region, then it doesn't matter because, well, it's a state, even though electrons travel faster, but inside the plasma region, it's basically a steady state, so they can maintain the neutrality. But towards the edge, where the electrodes are, there's a region that you just can't balance the charges, and this is a region where you have a much higher concentration of the positively charged ions, and this is actually now if we apply Gauss's law, if you have positive charged ions in it, it will build up a potential, and this is where the sheath potential is, and once the electrons coming in, the positive ion gets into it, it gets accelerated and strikes the substrate with high velocity and the directionality. Both are very important. All right. I have promised about the discussion about the high density plasma. So as we mentioned that for the normal density plasmas, it cannot sustain at very low pressure just because the charges gets a lot of the velocity, but it just doesn't find anywhere to fight with. Right? I want to fight, but nobody is near me. But what it does is that it will basically now not trying to disturb the positive ions, but what they do is they actually try to train the electrons, and we'll see what it does it do. So here we have the chamber. We have the chamber of the plasma, and now we're going to create a coil surrounding the chamber. And what we do next is that we are going to flow RF voltages. Basically we have a lot of the alternating current going through this coil. And if you think about it, we can use our right-hand rules. When the current goes, we will excite a magnetic field, and it can either go up if the current flowing this direction, and if it goes the other direction, the B goes down. So what happens is that we want to generate a magnetic field. More importantly, the magnetic field is time varying. It's not a static magnetic field, but it is a time varying magnetic field. So if you think about it, this magnetic field can increase in intensity and then decreasing and changing its direction, etc. So now you have oscillating magnetic field, and use Maxwell's equation or whatever is, it will actually in turn will generate an electric field, and in this case it's actually a circular electric field. The key thing is that this electric field is inside the vacuum chamber. So basically we are generating a circular electric field inside the chamber. And now what happens is that this electric field is not very strong. So basically for positively charged ions, basically, yeah, it's tiny. But for electrons, it's big enough because electrons are much lighter. And this, if you think about it, the electrons now are circulating like crazy. And this is important is that now the electrons are not leaving the scene. So basically, previously we think, okay, electrons, yeah, you shuttle through this plasma quickly without affecting anything. But now we ask it, say, okay, yeah, you can go, but now you are going in a sort of a corkscrew shape, and this will increase the chances of electrons colliding with the neutral atoms. And also, if it keep doing that, it will basically help ionizing the neutral atoms. And so what it is doing is that you can allow the plasma to sustain at a lower pressure, so it's almost 1 order of magnitude lower, so between 1 to 10 millitorrs. We can also adjust the plasma potential, which is the amount of energy that basically the ions strike the substrate, independent of the plasma density. So this is basically what we call the inductively coupled plasma, which is the main mechanism for high-density plasma tools. So we spend a lot of time discussing the plasmas. Then we want to say that now, because of this momentum and the energy of the ions, and when the ions now strike the substrate, it's like a bomb, right, hitting the substrate. So you can see that this is more like a high school physics. We're basically saying that, okay, the momentum basically transfer the most efficiently is when the two masses are of the same size. And that's why we argue that only the positively charged ions like argon does the actual work of dislodging the atoms from the substrate. The electrons, even though it has higher energy, a higher speed, because it's such a small, much lighter compared to the ions, it will not do a lot of damage to the substrate. So now we want to say that why we want a plasma in our PVD or physical vapor deposition, because the plasma will bombard the target with energetic ions like the argon, and then atoms at the surface are knocked loose. So basically what happens is that the plasma will create a shower of ions striking the target, and then the neutral atoms is going to be knocked loose out of the target, and the neutral atom can diffuse and deposit into the wafer, because only the neutral atoms can go against the plasma potential to reach the wafer. So we will see that there are also, you can deposit a lot of the metals like aluminum, tungsten, titanium. As we noticed, that tungsten is very difficult to evaporate because of its high melting temperature. So you can have DC or AC plasmas. So the sputtering process, as we have generally looked at it, and we know that the plasma will generate like the red ions, like argon, and then basically the target atoms basically are shown on like hollow white balls, right? So basically, when the ions hit the target, it will generate a lot of the dust, and the dust will contain the target atoms. But you can also have the argon atom, basically the argon receive an electron, and it will basically return to its original atomic stage. And then you also have the secondary electrons, etc., etc. So basically, we want to show that it's the process of sputtering deposition is that you have heavy inert gas in the major carrier like argon, and then you can also have reactive chemical species like oxygen may be introduced. So in this case, if you want to sputter, for example, aluminum oxide, then you will have a target of aluminum, and then you can introduce some gases like oxygen. And generally, you have low pressure, a few watts of power. You can do a substrate bias, in addition to the self bias, and you can also heat it up. So this is general process, and then we will also show that depending on how you connect the the target and the substrate, we can have both DC and AC. Given the limit on the amount of time we have, we will not go into detail what are the difference of the DC or AC. Generally, the argument is that the cathode or your anode, if they are not conducting, for example, then you need AC sputtering to sustain the plasma. It's a very elegant process, but we simply don't have time to cover it. We are doing some general comparison, even though we tried to give you an idea why we want to develop both technology. But we have some general comparison of the two methods. If you look at that, the major difference is that the deposition rate can be controlled in a wide range, but unfortunately, you can't really control very well, or very much the deposition rate. But generally, the sputtering process gives you better film quality, and this is the reason why the industry has been choosing the sputtering process over the evaporation. But evaporation is unique in that it can do lift-off and pattern, high, resolution patterns. Finally, the sputter process gives you better what we call a step edge coverage, because if you think about it, it's a neutral atom like a dust coming out in the plasma, and it can actually come to your substrate in many, many different angles. And if you want to have, for example, a metal, you really want the metal also to cover the sidewall, if you think about it, right? And this is the why. If you think about it, the integrated circuit industry, well, a lot of its businesses try to metallize the substrate, and that's why the step edge coverage is highly desirable, and the evaporation, unfortunately, does not provide very well the step coverages, and that's why another reason that for metallizations, the industry prefers the sputtering process. So I think that's the last one. I will see you on Friday.